In their infrared spectra, primary and secondary amines exhibit signals between 3350 and 3500 reciprocal centimeters. Now here on the slide it says 3300 to 3500, but again, you can always kind of take these numbers with a grain of salt. So we'll just say here between 3300 and 3500 reciprocal centimeters. And the signals that we see for an amine, the nitrogen-hydrogen stretching, is usually less intense than oxygen-hydrogen stretching that we would see in an alcohol or a carboxylic acid. And that is because the nitrogen-hydrogen bond is less polar than the oxygen-hydrogen bond. And if you go back to infrared spectroscopy, you might remember that the more polar a bond is, the stronger its absorbance will be in the infrared spectrum. Now, when it comes to amines that can have a nitrogen-hydrogen stretch, we can have a primary amine where we have a nitrogen that has two hydrogens attached to it, or we can have a secondary amine where we have two R groups attached to our nitrogen and only one hydrogen like this. And so with our primary amine, we're going to see two signals, right? Two nitrogen-hydrogen bonds, and therefore we see two NH stretches. And keep in mind that those are on account of symmetric and asymmetric stretching. And when it comes to secondary amines, we have only one stretch, right? Only one NH stretch because there's only one nitrogen-hydrogen bond, whereas tertiary amines do not give a nitrogen-hydrogen stretch. Why? Because a tertiary amine has three R groups on the nitrogen, and so there's no nitrogen-hydrogen bond, and so that's why we don't see that in the infrared spectrum. Now, tertiary amines, like you see right here, they do lack that nitrogen-hydrogen bond, as I was stating, and so they don't exhibit a signal between 3300 and 3500 reciprocal centimeters. However, a tertiary amine can be detected in an infrared spectrum by treating it with HCl, and so what's going to happen is it's going to be protonated to give you this trialkyl ammonium ion that you see here, and the resulting nitrogen-hydrogen bond that's formed does exhibit a characteristic signal between 2200 and 3000 reciprocal centimeters. In the proton NMR spectrum of an amine, any proton that's directly attached to the nitrogen atom, meaning for a primary or secondary amine, is typically going to appear as a broad signal somewhere between 0.5 and 5 parts per million. And the precise location of that signal is going to be sensitive to things like the solvent, the concentration of the sample, and temperature. And splitting is also not going to be observed for those protons, just like we saw with an alcohol, because they're labile and they're exchanged at a rate that's faster than the time scale of the NMR spectrometer. And also the broad signal for these protons can generally be removed from the spectrum by dissolving the amine in D2O, which results in a proton exchange. So it replaces the protons for deuterons, which don't show up in the NMR spectrum. Now, protons that are connected to the alpha position typically appear between 2 and 3 parts per million because of the deshielding effect of the nitrogen atom. So you guys know that the nitrogen is electron withdrawing. And so we see here for the alpha protons, we have a shift of around 2.7 parts per million in propylamine. And you notice that the deshielding effect of that nitrogen atom is greatest for the alpha protons. It tapers off with the beta protons, are only deshielded a little bit. They come out at around 1.5 parts per million. And then you can see for the gamma protons, they're not affected at all, being at 0.9 parts per million. In the carbon-13 NMR spectrum, we see something similar. The alpha carbon atoms typically appear between 30 and 50 parts per million, and that means they're shifted, about 20 parts per million downfield due to the deshielding effect of the nitrogen atom. So again, we have our nitrogen, which is a dipole, so it's pulling electron density away. You see our alpha carbon comes out at around 44.4 parts per million, and then you see the effect tapers off for the beta, which has a chemical shift of 27.1, and then essentially the gamma carbon is not affected at 11.4 parts per million. Now, you probably remember one of the most important rules in mass spectrometry was that compounds with an odd number of nitrogen atoms have an odd mass. Okay, so you want to remember the nitrogen rule. And then outside of the nitrogen rule, we also looked at alpha cleavage, which generates a radical and a resonance stabilized cation. So you should remember how alpha cleavage works. So you have your alpha carbon, okay, and then you can do a cleavage like this. And it could be here as well. They're just demonstrating it at this position. And the reason this happens is because we end up with a cation that's resonance stabilized.